Okay, so how is everyone today? Good, I hope. It's the week. It's nearly the weekend. Nearly there now. I'm ready. When we left last time, we were talking about Pascal's triangle. So we'll do one more of those and then move to something else. So for example, expand. How about 8p minus q to exponent 5 using Pascal's triangle. So, there's a homework posted about this, an online homework, one of the web browser thingy. And, I sent I gave a message also that said that the instructions on the web browser exercises say, instead of saying it exactly like this, they say something else. They say expand this thing using the binomial theorem. Well, and for our purposes, we're going to use Pascal's triangle. That's what we're going to do. You could, in my view, ask, well, why do they say it like that? Why do they say the binomial theorem? In the end, because like anything important, like Pascal's triangle, there's usually more than one way to look at it. And so there's like this sort of important abstract thing, math topic, and one of the ways is to look at it is with Pascal's triangle. If you're looking at it from the point of view of from probability and statistics, then you want to look at it usually from a point of view called the binomial theorem. But we're just going to do Pascal's triangle at this place. Okay, so that being said, so in such a exercise like that, written exercise, what's the first order of business?
Do Pascal's triangle.
Yeah, to write Pascal's triangle down. Down to what row? Fifth row. All right, so then, well, yeah, I mean there'll be 6 rows, but the row numbering starts with 0. So then it's got to be there because when the grader flips to your exercise and they're looking at it, if the grader doesn't see a big triangle of numbers, they're already not feeling good about this one, right? Okay. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Okay, and then so again, we discussed this last time. How do you know when you've gone the appropriate amount? Yeah. So then we need to get to the row whose number is 5. Now that is in some sense the 5th row if you start counting with 1, but that's row number 4. So the row that we're looking for is this one: 1, 5, 10, 10, 5, 1. Because there's that 5 we were looking for, like that. All right. So now, just as a reminder, this bit you would not need to write on an exercise, but since this is the first thing that we're doing today, I'll write it down, but mention that you don't need to write it unless it helps you. Our knowledge of Pascal's triangle is telling us that that means that a plus b to exponent 5 will have 6 terms, 1 for every coefficient in that row. And every one of the terms will have 5 letters, but a different mixture of letters. So the first term is when you have all A's, so that's A to 5. And then the next one is that we'll have 5, that coefficient, and then now we'll have 4 A's and a B. and then we'll have 10, and this time we'll have 3 A's and 2 B's, and then coefficient 10, and now we have 2 A's and 3 B's, and then coefficient 5, a single A and 4 B's, and then finally the last term, there's just 1 and it's all B's. Any question about this? So that's what it's saying there. Now, notably, you know, our knowledge says A plus B to exponent 5. Now this looks like, doesn't really look like A plus B. It looks more like A minus B. Looks more like A minus B. So, you know, what we're going to do is we're going to reckon this as looking this way, is that that will be something like 8p. Well, let me say it like this. We want to take that and make it fit this pattern. So something plus other something to exponent 5. We want it to be a plus in there so that we can use that idea. So like this. Okay, what goes in that one? 8p. And what goes in that one? Negative q. Right? So now, that's sort of like saying that, you know, you could say, here's one statement, subtract 7. Here's another statement, add negative 7. Okay, well, those mean the same thing, but, you know, humans being what we are, you know, everybody, it seems to me, strongly prefers to say subtract 7 rather than add negative 7. But they mean the same thing. So, you know, that's what I'm saying here. This says subtract q, but, you know, we're writing it down as add negative q. The purpose is so that we can end up using this formula. All right. What that's telling us is the following, is that 8p subtract q to exponent 5 will be that first thing, so 8p to exponent 5, and then plus 5, first thing to exponent 4, oops, 8p to exponent 4 multiplied by second thing, plus 10, the first thing, 8p to exponent 3 times the second thing, negative q, squared, like that. So I'm about halfway through writing these down. Is there any question where I'm getting this from? Any question about it? All right. Plus 10, and then the first thing squared, and the second thing cubed, and then plus 5, the first thing times the second thing to exponent 4, and then plus the second thing to exponent 5. So that's all 6 terms. And now, with these questions, you know, you always have to simplify it. Let's work on that. So concerning this one, how can we simplify that one? Specifically, what we want is we want to get like all the coefficient stuff to the front. Yeah, so that exponent 5 distributes over that product. So then that first one, you could write it as 8 to 5, p to 5. All right. Now with this one, well, we'd have that 5 there, so that'd be plus 5, and then now we have an 8. But the thing is because that 8 is in there, we actually have 4 8s, right? It's 8, 8, 8, 8. So that'd be to 4 there. And now, we've got letters P and Q, but there's actually, one more coefficient thing. There's that negative. So I'll write, multiplied by -1 there, and then P to 4Q. All right, continue. The next one, so this will be plus 10, and now that 3 distributes to there, and we'll get 8 to 3. And then, that negative also is there, so I'll write -1. But the thing about that -1 is how many of them are there? There's 2 of them, right? So that's -1 squared, -1 squared, and then p cubed q squared. You can always check your position, right? Because there we have p to 5, and then p to 4, and p to 3. So that's good. So we're going right. And we've got q to 1, q to 2. So the next one needs to have q to 3, right? Any question about getting here? So this really is just kind of the boring bit. But some of these technical details are important because, it's part of what's graded. So we'll have that 10. So 10, and then 8 squared, and then times -1 cubed, and then p squared, q cubed. All right, then plus that one. So that'd be 5 times 8 times -1 to exponent 4 times p times q to 4, and then plus -1 to exponent 5 q to 5. All right. So now the last order of business is just to figure out what those coefficients are. To multiply them out with your calculator or whatever. So for that one, 8 to exponent 5. I don't know. So 8 to exponent 5. So that's 32768. P to 5. All right. And then, so look at this second term. Because we've got that -1, that in the end, that means that we're not going to add the next term, we're going to subtract it. So it'll be subtract. And then I need to do 5 times 8 to 4. Which is 20,480. P to 4Q. Any questions so far? Okay, so then now plus, I need to simplify that. So 8 cubed is 512 times 10. Okay, and how about this negative? What's going to happen?
Squared, so it's going to negate itself.
Right, so it cancels away, so that means that we're going to add the next thing. Okay, so this will be 512 times 10, which is 5,120. And then p cubed q squared. All right. Then now we're going to have -1 to 3, to exponent 3. So we're going to subtract. So do you notice the pattern here? That it's add this one, subtract that one, add this one, subtract that one? Okay. Good. I lost where I was, right here. So this would be 64 times 10, so 640. P squared q cubed. -1 to exponent 4, well, that becomes just 1. That's 40. So that'd be plus 40 p times q to the 4th. And then finally, subtract q to 5. Any question about this one? So, you know, the coefficients, when you do a binomial expansion with Pascal's triangle, the coefficients, they just get wild and crazy. That's just how it is. No questions before we move to the next thing? All right. So, at this point, so we need a remark, and we'll call this, title this remark domain. So in the first place, so far in the semester, we've considered many kinds of expressions. Like, for example, these two. Like, how about x plus 13 over 2x minus 6. So there's one. And another one could be something like the square root of w plus 7. All right. So largely at this point, what we've done, as we said, we've done algebraic manipulations with those expressions. You know, things like, you know, expand, like we did on the previous page, you know, or factor, like we've done in some other cases, or, you know, get stuff, move stuff in and out of the radical, things like that. One of the things we can do, so one action that we can perform is to plug in values. So for example, I could say, for that one, I could say plug in x equal to 10, say. Into that one. So all that means is, you know, just take that expression, and everywhere you see an x, replace it with a 10, and then simplify the result. Okay. So then that'd be 10 plus 13 over 2 multiplied by 10, and then subtract 6. And then, you know, after some arithmetic, that'd be what, 23, and then over 14. Okay. Fine. Similarly, for this one, we could say something like plug in w is 11 into that one. Well, similar story. Square root of 11 plus 7, well, that'd be the square root of 18. Now, 18 doesn't have an integer square root, but it does have a square root. And we can simplify this a little bit according to our previous work by noticing that 18 factors as 2 multiplied by 9, and why is that helpful according to our previous work?
Because 9 is a square.
Yeah, because 9 does have an integer square root, so you could write it like this, maybe 3 square root of 2. Any question about that one? All right. Now back to this x thingy, this one. I could say, well, what about plug in x equal to 3? So just like, plug in x equal to 10, that means take that expression and everywhere you see x, replace with 10. Now I'm saying replace with 3. And the question is how are you supposed to respond to this request? All right. So 3 plus, in the numerator, 3 plus 13. And then in the denominator, that'd be 2 multiplied by 3, subtract 6. In the numerator, that'd be 16. And then in the denominator, that'd be 0, right? So what's the correct way to respond to this? Is to say, this is not defined. Not defined. It's not defined because it's a division by 0. All right. And over here, we could say something like, well, how about plug in W is, how about -9? What about that? Okay, well, similar story. -9 plus 7, well, that would be the square root of -2. And what's the correct way to respond to that? This is not defined. In the end, the reason over here is because this is division by 0, and the reason over here is because, remember we defined there's a radical for every for every natural greater than or equal to 2, and square root is radical number 2, and the behavior of the radicals depends on the parity, even versus odd. So square root is an even radical, and as a result, it has to have non-negative input. Or, saying it a different way, you can't put negative things in it. Okay, not defined, because, you could say no negative input for an even radical. All right. So what I want to point out by writing all this stuff down is that basically we've ignored the issue of what is permissible and what is not permissible, or if you like, what is defined and what is not defined to plug into an expression. We've just sort of ignored that issue until now. Now, basically, starting now and every lecture from now on, we're going to be very concerned with what you're allowed to plug in and what you're not allowed to plug in. So, when you give an expression, so the set of inputs for an expression is called the domain. All right, so now let's consider this carefully. So 2 examples side by side here. I could say let the square root of w plus 7, let that be our expression, with domain w W, say, greater than or equal to -3. And then in the right column, I'll say let our expression be square root of W plus 7 with domain W, how about W greater than or equal to 1? All right. So notice that that thingy is the same in both examples. So as a result, I can ask the following question. So plug in W is 11 for this one. All right. Well, we essentially did that right there. Okay, so I'll write that down. So this would be the square root of 11 plus 7, which is the square root of 18, which is 3 square root 2. Great. So now I'm going to ask this question over here in the right column. Plug in W is 11. All right. Well, for the third time, 11 plus 7, the square root of 11 plus 7 is the square root of 18, which is 3 square root 2. All right. Fine. 2. Now I'll say, how about plug in W is -2. All right. So now it's square root, and then everywhere I see W, I replace with -2. So I'll do -2, and then plus 7. Well, that's the square root of 5. And you know that 5 is prime, so we can't factor it any further. So we can't do any, fun stuff like we could with the 18. Any questions so far? Okay. So now here's the punchline. Over here in the right column, plug in W is -2. And what's the correct way to respond?
Not defined.
This is not defined. But to that, you might say, no, wait a second. We just did it right there. I thought we were just, for some reason, copying the same thing twice. No, we weren't. I mean, in some sense, we were. But the answer here is that this is not defined. Why not? Right. It says that the domain is W is greater than or equal to 1. Which means it's not allowed. It's not defined for you to plug in W is -2. Okay. Now, at first glance, at first blush, when you look at this, it kind of looks like this is just like some arbitrary thing we're saying, and to some extent it is. But to make a real world example, if you walk out the door and right over there to the vending machine, you can plug stuff into the vending machine, money, right? But it doesn't take like every kind of money. Now I haven't verified this, but I strongly suspect that I can't put a $100 bill in it. Probably not. That doesn't sound like something a vending machine would do. But it will accept things like quarters and like $1 bills and things like that. But it probably doesn't accept a Canadian quarter. if there even is one. I don't even know if there is one. But I know that they have coins, and I'm fairly sure that that vending machine won't accept them. So can you see that, yeah, okay, some machines, if we took that vending machine that's currently in North Texas and accepts U.S. denominated coins, and then we moved it over to, Canada, up north to Canada, then, you'd need to modify it and say that, okay, well, now you can use different kinds of coins. This is just some abstract way to say something like that. All right. So now, notice that on this one I said let this expression be with domain that, but up here and essentially every time until right here in the semester, we've written expressions but didn't say what the domain was. We just never said it. Okay. So now we need a rule for what it means when you write down an expression but you don't explicitly say what the domain is. So this rule and definition will be titled natural domain. All right. So first, the natural domain of an expression is the largest set of inputs for which the expression is defined. All right. So what I mean by that is an example of what I don't mean is we said this expression with that domain. Now that's surely not the natural domain. It's not the natural domain because ignoring issues of domain, is it possible to plug in w is -2? Yeah, you can. Because nothing breaks. But so that means that this domain is not the natural domain. All right. 2. When an expression is given. So when no explicit domain is given. The domain is the natural domain. So, what that means is that effectively, when I wrote this, and going backwards and looking at all the times that we wrote various things in the notes, when I wrote this and I never said the domain is whatever, that means that the domain of the expression that we're talking about is its natural domain. But down here, because the domain was explicitly written down, that is the domain. And then 3. Every explicit domain must be a subset of the natural domain. So that one's a little bit subtle. Really, in some sense, that third rule is sort of for me, mainly for me, and not for you. So what I mean to say is that this would be an error. If I gave you a question that said this, that said something like let this thing be given, w plus 7, with domain, say w greater than or equal to negative 1,314. So that would be saying that according to what I wrote there, it should be allowed for you to plug in negative 1,000. But can you plug in negative 1,000? No, because if you actually tried to put negative 1,000 right there, then there'd be a negative input into the radical. So all that that's saying, all that this third rule is saying, is that you can't like legislate the domain legislate away the domain of the square root. In the same kind of way that, you know, there's like a funny joke, and I don't know if it's a joke. I think it may be based off a true story. That, you know, you've got the circle constant pi 3.1415 whatever, and then you know, those digits they repeat. They go on forever and never repeat. It's just different numbers and just infinitely far. Okay, and you know that I suppose can be frustrating to a certain kind of person, but at any rate, as I understand it, one of the Indiana legislatures tried and almost passed a law defining pi to be exactly equal to 3. Well, you know, I mean, that's not gonna work, right? You can't just, you know, define away things. All right. So fine. Here's an example of this thing's use. So find the domain of that thing that we wrote on the previous page of x plus 13 over 2x minus 6. So did I give an explicit domain? No, right? I didn't say find the domain of this and then go on to write with domain that. If I did that, then you just have to just copy that that bit. All right. So there is no explicit domain. And therefore the domain is the natural domain. Which means we need to make a calculation. Now, the reason why I chose these two examples on the previous page is because at the present time, where the expressions that we're using are concerned, there's exactly two kinds of things that can go wrong. There'll be more things a little later, but right now we have just two. One of the things that can make an expression be undefined is a division by 0. The other thing is a negative input to an even radical. All right. So essentially, we're on a, you know, a search for any of those kinds of things. So you know, the idea we're looking for division by 0 or negative input to even radical. A little later, there'll be even more things you'll have to look out for. Okay. So that's nice in the sense that, well, this expression has no radicals in it. So there's no way we could accidentally put a negative thing into it because there isn't one. Right? So the only thing that could go wrong is division by 0. So the way that you show your work is like the following. Want to see you set up and solve something. So what we want to do is that if the denominator is ever 0, that's what would break it, right? That's what would break the evaluation. So what we want to do is we want to solve the following. Solve 2x minus 6 equal to 0. So, you know, the reason why we want to do that the idea here is that, because that's the denominator, that would be a division by 0. All right, so we want to solve this equation. All right, in the interest of time, I'll say, well, one way, a step in the right direction would be to add 6 to both sides. Doing that, we get 2x is 6. And then what? Divide by 2, both sides. Now we have x is 3. All right. So we set up an equation and solved it. Now the question is how do you interpret this? What does that mean?
That cannot be, that is not in our domain.
Right. Is that this is we haven't made any errors, so this is the list of all places that would cause a division by 0. So what this is a list of things that are not allowed. And the rule is that, natural domain is the largest set. So what that means is that everything that's not allowed is allowed. So as a result, everything that is not disallowed is what I'm trying to say is allowed. Therefore, the natural domain is all reals except x equal to 3. So you can plug anything in there except 3. You can plug in 33. You can plug in negative a million. You can plug in 3.000000004. That'd be fine. But not 3. Any question about this? All right. Next. So for example, find the domain of the square root of w plus 7. So again, same idea as before. So is the domain explicitly given? It isn't. So that means that the domain must be the natural domain. So no explicit domain. And therefore the domain is the natural domain. Which means we need to make a calculation. And again, there's exactly 2 kinds of things that can go wrong so far in the course for the expressions that we're limiting ourselves to. That is divisions by 0 and negative inputs to even radicals. So nicely, in this example, it's not possible to divide by 0, right? Because there's no divisions at all. So we don't need to worry about that. But we do need to worry about negative inputs to even radicals. All right. So in order to efficiently talk about this one, I'm going to introduce just a little bit of vocabulary, and that is that when you write the square root of x like that, so this is an idea. When you write the square root of x, the radical sort of represents something like a machine. So I'm going to keep using machine analogies in the sense that, like a vending machine is something the input is money, right? You put the money in and then something happens. And then, you put the thing in. So this thing put in the other thing. So the thing that gets put in the thing, that's kind of a clumsy statement. So, there's a nice math vocabulary word for that. And the name of the thing that gets put in the other thing is called argument. So argument. Now it doesn't mean quarreling. It doesn't mean that. So as a result, concerning the thing that we're actually looking at, square root of w plus 7, like that, we've got a radical, and what's the argument? It's w plus 7. All right. So that gives us a nice way to say what's required. So this thing that I'm covering up, it can't be negative. That's what we need. Another way to say it is that, so you could say the argument cannot be negative. So I'll say it like that. So argument cannot be negative. Okay, and then, slightly different ways to say that the argument must be non-negative. So now, many students would want to say, well, why don't you just say positive? Because there's a difference between positive and non-negative. What's the difference? Zero. All right. So then those ideas, here it is. We need to solve that the argument is non-negative. Argument is non-negative. Okay. So then, subtract 7. So that w is greater than or equal to negative 7. So we set up an inequality and solved it. Good. So the setup and solving of an equation or an inequality is, a big part of what's being graded. But now, how do you interpret this? So on the previous page, when we got to this position, we said that these are all the things that are not allowed. What are we saying here? So now these are all the things that are allowed. So you've got to be able to, look at it and make sure, is there an extra not? Is there an extra negation in there somewhere? So we can say, therefore, the natural domain is w greater than or equal to negative 7. So you could plug in w is 10. That'd be fine. You could plug in w is negative 6. Because if you did negative 6, that'd be negative 6 plus 7. That'd be 1. That'd be the square root of 1. All right. Last one. That we have this expression. So x squared plus 8x plus 16, and then all of that divided by x squared plus 11x plus 28. Let that be called A. Okay, then two requests. First, simplify A by cancellation. That's the first request. And the second request, find the domain of A. All right. So we're coming up against the clock, so I'm going to go through this part quick. And then I'm going to get to a point where I say, I really need your attention here. Here's the deal, is that, can we cancel, do these x squareds cancel? Do they cancel? No, they don't, right? They don't, because this is a division, right? That's a division. So they don't cancel like that. That's surely not a subtraction, so that doesn't work. Rather, what we need to do is we need to factor the numerator and denominator. And isn't it nice that the numerator and denominator are each monic quadratics? Isn't that nice? And isn't it nice that we're past those exercises where you've got to do that tedious thing, right? With monic quadratics. So would you please tell me, what are two numbers whose product is 16 and whose sum is 8? 4 and 4. So the numerator would factor like this, x plus 4 multiplied by x plus 4. And now can you tell me two numbers whose product is 28 and whose sum is 11?
7 and 4.
7 and 4. And now that we have this written this way, oops, that should be a 4. And here's a 4. All right, so now that we have it factored, do you observe that, oh yeah, those factors cancel. Those cancel. So simplify by cancellation. This is what this is what was requested in part 1. And now here's the part where I need you to pay close attention, because this is the place that students get messed up on a lot. The second question is find the natural domain of A, of expression A. Or find the domain of A. But because no domain was given, that means find the natural domain. So what is the domain of A? Alternatively, you could think of it like what's not allowed. Okay? So let me write, so I'll write that the natural domain is all reals except x equal -7. But this is not right. It's not right. Why is this not right?
Because we have a square. No.
This expression is expression A, that one. And if you plug in -7, the denominator will be 0. Is that the only way you can get the denominator to be 0? No, there's another way. What way? At -4. Can you plug -4 into there? Yeah. You'd have 0 over 3. That'd be fine. Can you plug -4 into that one? No. Or that one. So it's all x except this and this one. So it's this one that gets left off all the time. So last 10 seconds. I'm aware that many of you have seen this kind of thing before, this cancellation. But here's what I want you to observe that might not have been brought to your attention before this time, is that when you do that cancellation, this thing has its natural domain and this thing has its natural domain. And that cancellation can edit the domain. But the one that we were talking about is that one. So all the time students report that the domain is from that one, but that's not right. All right, so have a nice weekend.